check your settings. On, yes, let's do that. Record. And I'm trying to click on a lot of these and record. And let's go as far as we can. And another one. And another one. You're welcome, Dwan. Anybody else want the recording turned on? Record. Okay, you're welcome. And one more. I guess we're okay. Okay. We're making it. Where is it? Okay. Well, let me see. I had some class notes and where's my markers? Oh, I don't have them here. Okay. Stay where you are. Yeah. Okay, let's try this. Here, where's our camera? And there's a cable that gets in the way. Try here. That's almost right. Okay. Let's see. I have an agenda. About page 1, page 3. Well, here's what I want to do. I wish to make this a practice every class meeting, that the first 50 minutes is discussion on concepts. And the last 50 minutes is programming and practical things. I guess, what is it? The official word is open lab time. I really want to make it that. Okay. Some people say I'm hard to reach during the rest of the day, the rest of the week. It's unfortunate, that's the way it is, but here I am. I'm going to be here and take your questions about all kinds of programming issues, why things happen the way they do, and why we get, why do we move 0 into RAX before calling printf and stuff like that. So it's okay to ask me to fix your bugs. And it's okay to ask me to, why does stuff work the way it does? Why does it work? Okay. So let's go for the first 50 minutes. Did I get everybody's permission turned on who wants it? I'm glad to do it if there's anybody who I missed. Anybody? Okay. I hope we're all good to go here.
Wait, what? I'm sorry, I came in late. What happened?
I want to know if anybody wants the permission to record turned on.
Oh, okay.
That was the last thing I asked about. Okay. Some don't. It's okay if you don't want it. I have no problem. Okay. So let's begin on the first part. We're going for the first 50 minutes, and it makes long class meetings, but it's supposed to be, the administrators want it to be half teaching and half open lab doing things. Okay. So we're almost ready to conclude chapter 3. We've done that for the last 2 or 3 class meetings. We're coming to an end of it. And things you're supposed to know from chapter 3 are like this. Value of plus infinity or minus infinity. And you're supposed to know bias number and the special formula 1 with n zeros equals 2 to the n. I'll come back to that in a moment. And you're supposed to know the base number. And well, this is a tough one. S, smallest positive normal number. Where go with that? And which are, how do you distinguish normal numbers? Normal from the other 2 extremes, nans and subnormals. I can't get it all in, but you see it there. Okay, what else? All of this comes from chapter 3. Let's go back and make sure everyone has this in their records. Okay, what is positive infinity? Positive infinity is where you make the stored exponent as large as possible and the mantissa as small as possible. So it ends up looking like 0, 7, F. Now, if you look at that number, it's all ones, except the 7 has a leading 0, which means positive. But apart from that, the rest of it is all ones. And then you want to make this mantissa as small as possible. Okay, so looks like that. And 7FF means, well, 0 here is, that means the sign. Then there's the 7, 1, 1, 1. Then there's an F, and then there's an F. Okay. And that's the stored exponent. Why did I say F? There's a 1 there. 11 ones and a preceding 0 for the sign. Okay, and then I think we learned that this was all plus infinity was equal to 2 to the 1024. And then we did the math how to prove that. Okay, how do we make negative infinity? Negative infinity, you take this 0 and you change it to a 1 and keep everything else the same. And if that becomes a 1, then there's 4 ones. It's just another F. 0, F, 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 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is negative infinity, otherwise known as negative 2, 1024. Okay. Let's see, what else was, remember what was on the list here? Bias number, let's just insert it. That's 1023. And then there's an equation that says if you have a 1 followed by a lot of zeros, like n number of zeros, then that number becomes in base 10, it's simply 2 to the n. And that's a famous formula. We could actually dig it out and prove it, but now you know it. It's an easy formula. Okay. What else do you have to know from this chapter? How? Oh, base number. I better do that one. I don't think we did it here. Okay, so I'm going to use the paper in landscape. Well, in just 1 minute, I'll do that. Okay, so in a number line, 0.0 is here, and out here is plus infinity, and out here is the marker between normal numbers and subnormal numbers are this little piece here, and the nans are over here. Okay. There's this number here is often called, it's all the time called, smallest positive normal number. SPN. Okay, so it's sort of bound with plus infinity, those two bound in the normal numbers. Okay, so now I'm going to give you the definition of what are we talking about? The subnormal numbers, their stored exponent is always 0. Stored, I'm not in the camera, stored exponent. 1, 2, 3, 4, 5, 6, 7, 8. That's it. For infinity in the nans, stored exponent 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. So these are kind of like two special cases that are reserved for special uses. Special reserved exponent. And this one is too. Okay. Everything in the middle is normal exponent. Okay, now here comes the big picture. 0.0. Subnormals here. And then there's a boundary. All these normal numbers here. And then there's a boundary whose name is plus infinity. And then there's a few more nans out here. Okay. In the middle are the interesting ones. That's where we do our ordinary programming, is we use these in the middle between there and here. Okay. Now, a special number is going to fall out of this math, so watch for it to happen. Okay. Normal numbers, their exponent, I'm just going to use stored, is greater than 1 because it can't go down to 0. One. Okay. If it were 0, it'd be in the sub area. That we don't allow. And this way, on this direction, it can't be this exponent of infinity and his friends. It has to be up to 1 less than that. That would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. If the 0 were a 1, then it would be in the nan group. And if this 1 at this end were a 0, it would be in the subgroup. So it's the normals have their stored exponent caught between these two numbers. Okay. Next step. Remember the equation that stored exponent equals true exponent plus bias number. All right. So from this equation, if I subtract bias number from both sides of the equation, it will say stored exponent minus bias number is equal to the true exponent. This is kind of a complete thing. Stored exponent minus bias number is equal to true exponent. And I'm going to apply that to this inequality just above. I wish I hadn't written that there. It got in the way. Okay, we'll do it cleanly. Less than equal to stored is less than or equal to. Okay, now subtract the bias number from both sides, minus bias number, all three sides. In the middle, we'll have true exponent because of this equation up here. Okay, over here, I have to subtract the bias number 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, which our goal is to find what this one is. And then we have to subtract the bias number from over here, minus 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then we'll have the range. We'll know that the true exponents can't be smaller than this or larger than this. And then we'll move on to the next chapter. Okay, we've got to do this math. Any questions? Okay, I'll glance at the chat messages every once in a while. Let's do this math. I need my piece of paper. Okay. Okay, this one I'm pointing to on the left side over here is trying to subtract a large number from a small number. That's hard to do. So let's flip the subtraction over, subtract it in the reverse direction, and then put a minus sign with that answer. So it looks like this: 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, minus 1. That's an easy subtraction. But let's think about it. Can we? I'd like to do it in decimal. Isn't the bias number? Yeah, that's it. This is the bias number. We know what it is. It's 1023. And this one is easy to read. That's a 1. So this subtraction gives us 1022. But remember, it's upside down. I have to add a minus sign to this, and I'll have the final answer. So the real one is negative 1022. Okay. Now we work on the other side. That's got a problem too. Here's what we're trying to solve: 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, minus 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. The big number is on top, but this is that causes a problem. What can we do? I recommend this. Let's call this x. Let x equal this numerator. Okay. What is x plus 1? That's equal to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's, you had 1. Okay, so x plus 1 minus this denominator, well, that's not a denominator, minus this subtracting number. Well, you can see it. If you just put it directly underneath it, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. It all cancels out except the 1 on the, I don't have room to write this right here. There, what's left is this. I'm going under the camera. See, everything canceled except this 1 way back here. And the rule we had is if you have a 1 followed by a certain number of zeros, we know that that's 2 to the, there's 10 zeros, 1024. Okay, but the problem is I added 1 in order to make this math easier. So the real x is, the real answer is 1 smaller than what I really computed. 23. Okay, I don't know if you're still following. This is 1023. Okay, so here's the summary. What it's saying to us is that for normal numbers, the range of exponents is given to us there. For normal numbers, the exponent will, the true exponents will be in the range -1022 ... positive 1023. And this one, there it is. This one is called base number. Base number. It's not as famous as its partner, the bias number. Bias number. Okay, so if you have a number in scientific form, 1.10111 times 2 to the 1029, that number is not going to fit in the register because 1029 is out of bounds. If you have a nice number like 1001 times 2 to the 500, can that be stored in your 64-bit register? Yes. 500 is between the low and the high. No problem. So no, yes. And what if you had a number that's really small? This exponent is smaller than the smallest one we have to work with. This is going to fail. It cannot be stored in a 64-bit register. That's the outcome of these two bounds. Okay, I'm going to move on. You got your notes for the big day coming. Okay, what's on the agenda? It's okay. I want to address okay, let's look at, the declaring constants. We're actually in chapter 4 now. Chapter 4, the title is Program Format. How do you lay out an assembly program? And I think you know already 2/3 of this chapter, so it should be kind of easy. How do you lay it out is at the beginning, not counting comments, but at the beginning, there's a section where you declare constants and globals. There's usually one of these. External functions, they're not in a section or a segment. They're just declared at the very beginning of the source code. Okay, so I want to deal with this guy. Constants lets you name numbers. Upper limit is to represent 500. No problem. There is a problem with decimal points. Okay. Before I go, I'm going to jump to that in a moment. But what is kind of strange, there is no size requirement on these constants. You don't have to specify this is in a word size register, or this is in a double word register. 32 bits here, 16 here. You don't have to specify anything about it. You just go ahead and use it. Now, bite-sized registers max out at 255. Their range is from negative 250. I think I get this. I hope I got this right. Oh no. Let me think. No, I take it back. Their range is from negative 127 up to positive 128. No, it's the other way around. Negative 128 to positive 127. Okay, so this number is too big to fit in there. You can't say move. You remember it's called AL, comma, upper limit. It doesn't work. This only has 8 bits. You need more than 8 bits to store 500. The assembler will give you error messages here. But you could move it into a 16-bit register. That's plain old AX, upper limit. And the machine understands that. Then you can move it into a 32-bit register, EAX. Machine understands that. Or 64. It's an MOV. So here, MOV, RAX, upper limit. Okay, so this thing defines data values without, I don't know how it does it. Without mentioning the size. Is it an 8-bit number? Is it 16, 32, or 64? It all works, like all 3 of these work. For 16 bits, 32, and 64. All that's required is that the number fit. Okay, now, there's a problem with decimal numbers. Making a constant name for it. One of your programs was to use the gravitational constant. Gravity EQU 9.8. Okay. But there's a problem. The dot is not approved. These constants don't like dots in the specification. So what do you do for float numbers? Integers are like back here. There's no issue at all. But for constants, for constant float numbers, there's a problem. What it wants is, it wants the IEEE form of that constant. Okay, so we got to replace this with IEEE and it'll all work. Okay, so what did you learn last week? You learned how to make IEEE numbers. You ready? We're going to do it right now. Okay, 9.8. We take away the 9, and that's 1001. We look at the 0.8, and you see if visually you can make it look like a sum of 1/2 to the first plus 1/2 to the second plus 1/2 to the third plus 1/2 to the fourth, but nothing like that jumps out at you. If it were 0.75, you can say that's 1/2 to the first plus 1/2 squared. And that's true. And so 0.75 is equal to 0.11 in binary. There's invisible ones in front of you. Okay, but we have the 0.8 problem. 0.8 times 2, we're going to do it the long way, 1.6. 0.6 times 2, 1.2. 0.2 times 2, 0.4. 0.4 times 2, 0.8. 0.8 times 2, 1.6. And now you see what's happening. This group is starting to repeat itself. So we're on the verge of discovery what 0.8 is. 0.8 are these little numbers on the left side of the dot. 0.1100, 1100, 1100. Like so. Let's put it all together. 9.8 equals 1001.1100.1100.00. Okay, that's a big milestone because that's science. No, it's not scientific. We have to take this over to here. Okay. So it now will become scientific. 1.00111001100110011 times 2 to the 3 because I moved the dot 3 places. Okay. Now we're making good progress. We take the 3 and add the bias number. Can we do this in hex? 3 is already a hex number. The bias number is 10 ones. Like such. Okay, you count on your fingers. You're adding F plus 3. So you say F 10, 11, 12. The answer is 12. You write 2 and you carry 1. Now you're at F and you add 1. F, 1 larger is 10. So you write 0 and you carry 1. 1 plus 3 is a nice 4. And now we have the stored exponent. Okay, I think we're just about ready to write down our number, except I want to use a color to mark it off in groups of 4 for easier reading. And the one next to that is a 9. And another 9. Another 9. And they're all 9s, except we have a small problem here on the last digit. the last digit. I'm going to leave a gap there. I'm going to fill it in right now. Something goes here, but these nines in math theory continue forever. Okay, we're only allowed for 16 digits and the register's full. That's up to there. So what you do is, and the machine does it for us, is you look at the next digit that's outside the register and ask yourself, is it 8 or larger? If it's 8 or larger, you add 1 to what would have been over here. If it's 7 or smaller, you don't add 1 to what should be over here. Okay, but we have a 9. 9 is obviously greater than equal to 8. Therefore, I don't put a 9 here. I put the next digit higher, which is a, anyone want to guess? What is 9 plus 1? Nobody's guessing. Okay.
10.
No, it's not 10. Try again.
You said 9 plus 1?
9 plus 1.
Or 0. You put 0.
You, it's not quite right. 7, 8, 9. The next one is hey.
Hey,
Hey, it said in chat.
Oh, I wasn't looking. Yeah, thanks, Joseph. I looked up now. So you round up the 9 to the next digit higher, which would be A, and then you throw away these. They don't go in the register. Okay, that's the number you need in that assignment where it's doing gravity. 4023. And now you saw how it came about. 9999, 9999, 9999A. Okay. Sometimes I mix you up with the morning class. I may have done this already, but I hope not. But you saw it a second time. And it's good practice to convert decimal numbers like 9.8 into hex numbers like the one up above. Okay, let's see what is on the agenda here. Trying to get, I'm trying to come up with something useful here. What's our time? We went, we got a little bit more time. 10 more minutes, then we're going to switch gears. I want to hear from you what kind of issues you have with the programming. In this coming chapter, it talks about compiling and linking and those matters. So let's talk about, well, I'll finish these last 10 minutes on this subject. G++ is an open source compiler for C++. Compile. And because it was made by the GNU organization, GNU, I'm very, very sure what they did was take C++ and change the C to their first letter, and it became G++. That's okay. It's very reliable and stable compiler. And if you're compiling C language, it's this one. Same effect. The little c twice means we're compiling C language. All right. Now, there's some things we attach to the end of these. And as far as I know, they apply to both. Okay, so some of the things are a small c, a hyphen and a small c. The meaning of this is, I'll explain what. Compile and assemble. Compile and assemble. But don't link. And as opposed to that, a hyphen uppercase S means compile, but don't, and not assemble. Assemble. I'm going to draw a diagram in a few minutes and make this clear what that means. There's something called PIE, Position Independent Executable. Executable. Double. Wait a second. That can't be. There's somebody knocking on this door here. I don't know. Should I open the door? I'm teaching right now. Class, just hang with me. We're in class session right now. I don't want to answer the doorbell. Okay. Position independent code is really outside the realm of assembly programming. It's how the loader can put the executable file in memory at any position it wants. But that's not our concern. Our concern is that G++ can output an object file in this category or not in this category. So when we say G++ -C -standard C++17, and then we say we're going to compile something. O is triangle.o, and then we're compiling triangle.cpp. So by not saying anything, this assumes that you want PIE, you want pi. However, speaking of this one, the object file that's created by the compiler, the output file, do you want it to be in the category of PIE or not in the category of PIE? And you have a choice. You can put in there -no PIE. And that turns it off so that this output will not be in the PIE category, or you can leave it out completely, and then this output will be in the PIE category. If you're writing all C++, you probably don't care. Our issue is NASM only makes no pi. When you compile with NASM, you have something like ELF here, and then -O. We need a name here. Angle.o, and you're compiling the file angle.asm. The way NASM is set up, it only makes no pi output. This is the output file. Okay. For all of these to be linkable together, they have to be either all no pi's or all pi's. Okay. You follow that? So we're going to have a lot of statements: a G++ statement, a NASM statement, a GCC statement, another G++ statement, and they all make object files like the ones in circle. We want them to be all of the same type, but NASM only makes no pi's. Therefore, all the others have to be no pi also. That's why this guy is here. What good it actually does for you, I'm not an expert on that. That's for operating system class or someplace else. Okay, we just know that they all have to be of the no pi type. All right. In NASM, you don't put anything about pi. They're already of the no pi type. All the others, you have to put this no pi. Okay, so you do several of these statements, and then at the very end, you link, there's a linking statement that combines all the object files, this one and others that you may have, to one file that can actually execute. Okay, now I promised I'd explain this back here. Let me switch colors. Let's say you start out with a C++ main program. This is drive.cpp. Okay. And you compile it with G++. And believe it or not, it goes through two steps that we don't see. I mean, it turns that into an assembly file. drive.asm. And then it goes on, the same operation goes on to create drive.o file. Okay. So here's ordinary C++. There's a main. You call the compiler, and it creates assembly stuff, segment, text, and the whole shot in here. And then this same guy has the capability of assembling. It keeps on going, and it creates an object file, which is linkable. This is totally binary. Humans can't read it. Or not easily can't read it. Okay. This is some kind of assembly that looks horrible. I'm going to show it to you someday, very soon. We'll actually do the test. This one is just horrible looking assembly. I shouldn't say that, but it is. We're going to see it, and I'll tell you why. Okay, so if you compile the C++ G with G++ and you include a hyphen little c, it takes you all the, here it says compile it and assemble it, don't link it. It means it goes all the way, creates this one, and from there it creates this one, and it's got it's created, compiled it, and it's to this, and then it's assembled this into this, and there it pauses. If you use G++ hyphen uppercase S and all the stuff after it, it just compiles to here and stops. You end up with an assembly version of what you had over here. Okay, that's what I'm trying to explain, why these two are different. The little c is what we normally use in this course. You compile it and you assemble it, and the output is an object file. Okay. We'll experiment with it. If you use uppercase S, it will compile it and create an assembly program and stop there. The output will be this one right here. Now you know about position independent things, why we keep it there as no pi. That's to make it all linkable. That's its only reason for being there, is that it could be linkable with other object files. And we're quickly running out of time. Let's see, I have one more. Pi, S pi, no pi. No, and okay, I'll conclude with this one, and we'll go to programming issues. In the lifetime of C++, Barnes Strostrup created this whole thing. I think I can't ever spell it. Strostrup. Yes. I ruined the guy's name. I don't know. I don't know how to spell it. I don't know how to say it. He built this C++, and the standard keeps changing every 4 or 5 years. And I looked it up earlier today. The earliest standard I could find online was C++ 1998, 2003, C++ 2011, C++ 14, 2014, C++ 2017, C++ 2020, but it's sometimes known as C++ 2A. I don't know why. Okay. So if in your corporation, if you're working, there's several teams working on a same large project, your team leaders have to all have a meeting and get together and say, we're all using the same standard. Like, we'll all work on this. If part of the files are compiled under standard 14 and others under standard 20, they're not going to link at the end. You got to all come together to a common standard you want to work on. If you're repairing an old program that was built under 2014 standard and you're fixing things, you want to stay in that same standard and keep compiling using 2014 standard. Okay, so it looks like I'm hitting on triviality, but in the corporate world of software development, it is important. So your compiling line looks like little c, little M64. It says my target machine is a 64-bit one, and somewhere you should say standard equals C++ like 17. I've tried 20. It's our current, my G++ is not updated to 20, but it does have this one. I don't know what's going on there. Or I use 2017. It's all built in. All those standards are built into here. It can all do any of them, but you have to pick one and kind of stick with it. And then they'll be all, the output files will all be compatible with each other. Got it? Okay. That's from a chapter coming very soon, but we had 10-minute preview about it. Okay, class. The assembly is not easy. Assembly programming is not easy. You must have some kind of issues that I could help with. I think it's great when you learn from each other, you share information. BJ Rain. Thanks, Joseph. Okay. What was the question? I didn't get it, Joseph. Well, the A question mark, but that's, maybe I don't get it. Okay. Here's some stuff what we do. Programming. Move RAX 0. Move RDI new form. Form. Okay, move an integer into RSI, comma, came from R15, and we call printf. Okay, and there's a block to set up an output statement. Okay, in its assembly form, there's 4 statements there. In C++, it would be 1, I think. I don't know. You see out something. See out my number. It's not a fair comparison, but C++ generally has like one statement to 4 or 5 assembly instructions to do the same thing. Okay, here's the question is, you put that in your program and you read it and it's absolutely perfect. And you compile your program and you run it, but it crashes here. Segfault is the official term for it. You ask a classmate, how did you print this number I'm saving? And it shows you his program. And it looks exactly the same, and it works. His works absolutely fine. Yours don't. Yours is the exact same statements. You could have taken a photograph and pasted it over in your program, and it'd be exactly the same, but yours doesn't work. What's going on? Barnes, oh, Strup, like STRU, Strup. Thank you. Okay, all my life I could never get it right, but he's a great genius somewhere, and I'm pretty sure he lives in Europe, but so take it for what it's worth. He created a language that's probably the best learning tool there is among all of them. Okay, so I'm leading up to something. When you get that error message, segfault, blah, blah, yeah, a bunch of garbage around it, and you go back to your program and you look for the last line of output that you saw, something before this. It was a printf and executed correctly. Okay, but when you get to this one, it doesn't execute. The reason is called the 16-byte boundary problem. 16-byte boundary. Okay, and common speech among programmers is that if you're getting this segfault, you're off the 16-byte boundary. And sometimes they don't even say the number 16, you just say off the boundary. Okay, how does that happen? It happens that it has to do with the top of the stack. Here is, the top is at the bottom, of course. This is where RSP is. RSP holds the address at the top. 1440. Okay, so 1440. One above that, we add 8 because every quad word has 8 bytes. 1450. That readable? I hope. 1458. 1460. 1468, and so on. I'm adding 8 each time. 8 plus 8 is 10. So it goes to 0 and the 1 carries over next to it. 0 plus 8 is 8. 8 plus 8 is 0. It's actually 10, but the 1 gets included with the 5 goes to 6. So I'm counting by 8s going up to higher addresses. In old days, the programmers created library functions. Printf, fgets, scanf. Do we have any others? I'm sure there's others I can't think of. Get char. Okay, those are library functions. They've been programmed 10 years or 15, 19 years ago for reasons I'm not fully sure of, but I've read about them. These programmers used the requirement that RSP must be divisible evenly by 16. By 16. 16, that's a decimal number, or if you like in hex, it's 10. It's built into the code, and most of them did this. I don't, and again, I say I don't fully understand why, but it's old history. These functions, and there's dozens of them in common libraries, have already been programmed. Nobody's going to go back and change it now. So to be divisible by 10 in hex or 16 in decimal, it means it has to end in a 0. And if it happens to end in an 8 and you call one of these library functions, then it crashes with a segfault. Understand that's the cause of it. The cause of these, of the errors I'm talking about, called the boundary errors, is when at the time you call a function, like right here, at the moment you're calling this function, if RSP is holding a number that ends in 0, a hex number that ends in 0, it's good to go. If it's holding a hex number that ends in non-zero, usually that's an 8, it will crash. And people say, I was off the boundary and it crashed. So how do we fix that? We get on the boundary and then do the printf and then get back off. I'll put it here. You say push keyword 0, and it actually turns out you can just put any number there. The 0 is not important. The important part is the keyword is 8 bytes, and that would actually, it subtracts 8 and you get a smaller number, and then you get a new top of stack. Okay, then you go through the usual stuff. Move RAX 0, move RDI form, move RSI R15, call printf. But see, now this, if you were off the boundary and then you did this, it puts you on the boundary, and then you can go through all your stuff and get the output accomplished. But as good programmer, you clean up the mess after you're done with it. So we put it back where it was originally. And these two counteract each other. So you get on the boundary, do all the work, and then get back to where you were earlier. It's good programming practice to restore the stack back to its original state whenever you use it. Okay. Let's see. So what my practice is, I program assuming I'm on the boundary all the time. So I write the original program, and this is not present. And this is not present. And then I run it. And if I get this, you do it enough times, you'll recognize it. You'll get this segfault problem in the middle of a run. You find out where was the last good output, last good printf, and the next one is the one that has the problem. Do a push and a pop around this block, and it will work. And that fixes it. Okay. All of these are dependent upon this boundary problem. So you try it first with no push and pop, but later you may have to put the push and pop in there. Okay. Some other student asked me earlier today, why the RAX 0. The last word on this is, when you do the push, you can put 64 little tiny zeros in there if you want, but it doesn't have to be 0. You could just push 17 or some other number in there. It'll go in as binary, 000100001 or something. So this 0 has no great importance. Just any number will do the job there. Okay. Why do we do the move RAX to 0? It's to tell the function that's going to be called that there are no XMM registers involved. That's in words, that's what it means. It's a signal to the called function no XMM are part of this call, in the call. Okay, and some students have told me, well, right here's an example. I took it out and it still works. Yeah, I think you're just lucky. Half the time you can take it out and it still works. But as a good programming habit, you should probably keep that. Whenever this printf does not have to go get any numbers out of XMM registers, it's a good practice to keep it here. Then the day will come when you do need it, you'll remember it. What if printf is going to output 2 float numbers? Printf. Now let's do this one. And I'm interested to hear your kind of questions, so I'll keep this down to 2 more minutes. Suppose your form says percent 10.2 LF space over percent 6 LD space over percent 7.1 LF 0. Okay. That form wants 3 numbers. It wants a float number here, an integer number here, and a float number here. So you, the programmer, you know you need 2 float numbers. The first thing you probably want to do, first thing I recommend is move RAX a 2. That's the signal to printf, hey, be aware, 2 float numbers are going to be needed. Now you go through all the rest of it. Move RDI form. Now, this first float number has to be XMM 0. XMM 0. XMM, it came from somewhere, XMM 14. The next number is going to be an integer. That has to be RSI. Comma, we don't know where it came from, R15. The third value is another float. It has to be XMM1. One, comma, wherever you had it stored. And we're set to go. And that will output 3 numbers all in one line, formatted like that. What do you do if this crashes? It looks perfectly good to me in printed form. If it crashes, the first thing you should try is push Q word, make up your favorite number. 99, and pop Q, pop RAS. And then I'm not saying it takes care of 100% of the cases, but it will take care of 99.9% of the cases where you have a seg fault due to this block. You'll be off the boundary. Okay, anybody have a question about your own programming that I can focus on and help everybody learn from it at the same time? That's my biggest goal. You doing okay with dropping a marble out of a tall building, or computing the square root? I think the marble problem had a square root issue in it. Remember that you shouldn't call the function called square root. You should use the instruction called square root. SQRT, just because of speed. You don't want to, in the math library, there is SQRT, and you could do a block setup and get your answer that way. The issue is that's so slow. In comparative speed, this is a snail crawling on the sidewalk, and this is a car driving by the street. So use instructions that are part of the CPU first, and when those aren't available, then you go off and get library functions. Okay. Can I help anybody? Well, okay. I think as always, I'm going to be here till 10 minutes to 4. I hope you have a good afternoon and a good evening. And if you're still hanging around during the next 25 minutes, next 45 minutes, I'll be here. You can ask me. And keep on learning, everybody. Have a nice afternoon, all of you. I'm glad you came. Goodbye.